In this video, we are going to briefly discuss the PCOMPLS entry for MSC Nastran. Now, there are two things I want to discuss. Number one, how do you format the PCOMPLS entry? And then number two, some considerations regarding the material coordinate system. It's very important that you use the shortcut as much as possible to define the material coordinate system. If you don't use the shortcut, you might be having to use thousands of coordinate systems to properly align your elastic tensor, your stiffness tensor, your elasticity tensor. So again, for 3D elements, you have to orient. What's going on here? You have to orient your tensor here. Does the x direction go up and down, in and out, left and right? So that's why we have to take into account the material coordinate system. So I'll get to that in a moment. So let's first talk about the PCOMPLS entry. So let's go ahead and import an existing example with PCOMPLS. So here, let's see, what entry was that? Oh, I don't think, oh, here it is. So let's go ahead and maybe turn this off, change the background color, and let's open the web app. Oh, right. So the web apps we're using today are available at theengineeringlab.com. Here at the top right hand corner, you have a blue button saying free trial pre-post web app. You can click that link, fill out the form, and you'll get access to the pre-web app. Okay, so here, let's go ahead and open the PCOMPLS entries. So here we have one PCOMPLS entries. We have a table defining all the layers in this PCOMPLS entry. So let's go ahead and move this to the right maybe. Let's add one additional row. So row 6 or layer 6. Let's go and give it a gply ID. So we'll give it a gply ID of 1. We'll give it a material. And then for the angle, we'll give it 0. And let's give the first row layer angle of 90. So this is layer 1. Layer 2, layer 3, 4, 5, and 6. So here if we look at the screen, this red layer, this is the first layer. Then we have layer 2, 3, 4, 5, and 6. You'll notice one thing. Let me exit this. Let me go to LBCs and turn off let me turn off everything actually. So these are the hexahedral elements. This PCOMPLS, this is a preview of all the different rows. I think it might help if I turn off the element edges. Okay, yeah. So here are the layers. But there's one small problem right now. The newest layer that we created, it's going beyond the thickness of the element. So why is that happening? That's because right now we're using this option. Let me see if I can find it. Oh, I think the option is blank. Right now it's blank. It's using the 1 option, I believe, by default. If you click on the description, this would give you more descriptions of what's going on here. Okay, so what does direct 1, 2, and 3 mean? More importantly, what's the default? Here the default is +1. So here, this is the default. When you use direct equals +1, 2, or 3, what's going on, it's going to use a fraction of the element thickness to determine the thickness of that layer. So as an example, let's suppose the thickness of the layer was maybe 1 meter, as an example, 1 meter. So here in the thickness here, let's go ahead and scroll to the far right. Here for TI, these are actually fractional values of the total element thickness if you use positive for direct. So here, say direct equals +1, +2, +3, or same thing, 1, 2, or 3. They're the same thing. What does this mean? TI are fractional thickness, element thickness values. So suppose that the element thickness was 1 meter as an example, and T1 is equal to 0.2, T2 is equal to 0.2, and so on and so on. So T1 actually has a thickness of 1 meter times 0.2, which is 0.2 meters. Now we'll do this again and again. So 2, 3, 4, 5, and 6. So here, each layer now has a fraction of the total thickness. Now, let's sum it up. What is the total layer thickness, what's the total thickness of our laminate, if you will? It's 1.2 meters. But that's a problem because our element thickness is 1.0 meters. So now you decide, do you want to use +1, +2, +3, or do you want to use a different approach? A direct equals -1, -2, or -3. So what happens here? The thickness is actual units of length. So here, if you use positive, your TI values are fractional values. If you use negative, these are actual thickness values of a length. So I'll leave it up to you to decide. Do you want to use fractional values, or do you want to use actual units of length for the thickness values? So here, what would we do in this case? We would take the thickness of the element, maybe 1 meter. I don't know what 1 divided by 6 is off the top of my head. So it's a 0.166. So what we can do back in the web app, we'll say use 0.0166 for each fraction, and you'll see that the thickness is adjusted automatically. So you see that. So before we were using 0.2, and maybe I'll color the last layer. The last layer is maybe, I don't know, 5 degrees. And we'll use 0.2 before. So you see that? For these golden layers and the red layer, this is the actual element thickness. And then the brown layer, which is the last layer, it's actually going beyond the element thickness. Do you want this? Do you not want this? This is a question. I'll leave it up to you. In my opinion, it may or may not matter, because the stiffness of these 6 layers gets reduced to just these elements. So if you want, you can actually squeeze 100 elements that will go beyond the element thickness, but it all gets reduced to the thickness at a single element. So here, I'll give you an example. Suppose we created a lot of rows, and here we'll use a 0.2 for all of these. So here you can see that we have a lot more layers. All these layers, the stiffness gets reduced to a stiffness at the element. So you could, if you wanted to, you could stuff 1,000,000 layers in that one element. It still gets condensed to that one element. So let's go back to the pre-web app, and let's go ahead and delete some of these layers and continue our discussion. So delete 12, 14, and I think we only had 6 layers. So let's go back here. Okay, let's go ahead and now adjust this. I think a moment ago we were using 0.0166. Okay, so you could do that. Now, let's go ahead and switch to a different option. So right now we've selected 1 or +1. That's using fractional values to determine the thickness of the layer. Let's use -1. And now we are responsible for supplying actual thickness values. So let's go ahead and do this. I actually don't know what the thickness of that element is. So let's do this. So here we're using a thickness of 0.01. So if this was in millimeters, these layers are in literal units of length, or 0.01 meters. I believe we have a option to display the distance. So let's do this. Let's open Fem label. We'll display the thickness of the faces. Let's go to Fem label and pick some nodes. Oh, well, we'll have to go ahead and pick some elements and display the corresponding grids. Let's see if this works. Oh, right, this might be a little difficult. Okay, so at the time of creating this video, I don't have a way to show the element thickness. So we'll have to go about this through trial and error, trying to figure out what's a good thickness to use for the layers. So maybe 0.1. Oh, okay. So maybe is the thickness exactly 1? It might be pure coincidence. Oh, no, it's not. So again, I'm going through this trial and error process. Okay, so it's not that. Let's try 6 maybe. And 5. What's going on here? 0.05. Let's try that again. So I should have done this before the tutorial, but unfortunately I didn't. Okay, so I think we're getting closer. So maybe 0.03. Let's try 6. 8. Right, so we're hovering around, what is this? 1, 2, 3, 4, 5, and 6. So let's say what's the thickness of this element? So the thickness is about 0.05. Okay, so that's the actual thickness of the element, so divided by 6. So each layer should have a thickness of maybe 0.0833 millimeters. Okay, so a few more things. The direct, you'll have 3 options for the direct. 1, 2, or 3. What do these different values mean? So you could either build your layers by stacking, starting from these element faces or the other element faces. So here, let's go ahead and use maybe -2. And let's turn off this here. I got a lot going on here, so let's see if we can. Oh, I think I built my, I think, let me go back to fractional values. This is getting complicated. Part of the confusion is that I don't know what the actual thickness of that element is, so that's adding to my confusion here. Okay, so let's look at it like this, and now let's go ahead and experiment with the direction field. So right now this is direction field, direction 1, and then this is the second option. So what we're saying is, before we were starting from the underside, we were starting from this face here, and we started from this face and started stacking our layers, if you will. But now when we use the second option, we're saying, you know what, use this face and start stacking the layers. So this is layer 1, layer 2, 3, 4, 5, and 6. And the third option, this is going to use a different face of the element. So now our layers are from this face and on. So this is layer 1, 2, 3, 4, 5, and 6. Okay, now what if you had bending here? Bending, maybe you had it fixed on one end, and then there's a force going in the positive z direction. What would you do there? You would need to add more elements to the thickness. So maybe you would have elements 1, 2, 4, 5, and 6 as an example, and then you would need to configure the PCOMPLS for that. Here, if I wanted to, I could actually load this in bending. I would fix this here. And actually, maybe we have time to do that. Maybe I should try that. Right, so let's try it. Let's see if we get lucky today. Okay, so let's go ahead and jump out of here. Let's do one thing. Let's make sure this runs. It's very common that we try and it doesn't run. So let's go ahead and run Nastran. And I noticed one thing. We're still in development with this pre-web app. So we're not going to be able to get Okay, for positive values, the direct sum of the ply thicknesses must be 1.0. Okay, that's an interesting error. So we're still developing this capability for the PCOMPLS entry. One thing we won't be able to look at are the deformations and stresses. So let's just try and get something that runs. We see that we get a user fatal message here saying that, hey, the total thickness is not equal to 1. Let me read this message a little bit more. So has a positive value in the direct, but the sum of the ply thicknesses is 0.999. For positive values, the sum of the ply thicknesses must be 1. I think this means that the sum of the fractional values must be 1. So let's do this. Let's go back here. Oh, I'm getting my bearings mixed up. Let's do this. Let's do an inspection. So here I clicked inspect to see if we get the same error, and unfortunately we don't. That's okay. So let's go back to bulk, go to select and PCOMPLS. Let's go here to the far right. Let's try and use 7. I wish there was a way to relax that constraint. It wants us to have a total fractional value of 1. But, you know, it's really difficult to get an exact value of 1. So here, you can see that we are very, very close to 1. And we're still getting these errors, which I'm not a big fan of. So let me do this. Let me take a step back. Let me delete layer 6. And let me use 0.2 as a fraction. And now let's try and rerun Nastran. And then I believe that was a success. Okay, so it's complete. So the error went away. So that's a lesson learned. Don't use... there's a word for that. I forget what the word is. For numbers that run on, I guess Nastran is not going to like that, so we'll have to use very precise values here. If there are any mathematicians out there, I forget what the name is, but there's a name for numbers who can be expressed in terms of integers. Here as an example, this could be 1.0 divided by 5. That will lead to this. But this, I believe, there are no integers that would give you that, or I guess it would be 1 and 3. So disregard what I said a moment ago. An important story is that we see that there is sort of a challenge there where when using fractional values for the thicknesses, but it's okay. Here we've performed a statics analysis successfully for this. I don't know if we'll get displacements here, but we'll see. Oh, we actually do get displacements. So yeah, we've successfully analyzed this configuration here. So if I wanted to, let's go ahead and build this. Let me look at this. Let's go ahead and do this. Let me delete the SPCs. So I'm going off script at this point, but this might be beneficial to you. Let's go ahead and delete some of the SPC ones. Let's just go ahead and delete all of these. Let's create a new one. We'll go ahead and constrain all of them. All 3 degrees of freedom. Let's go ahead and turn off the preview. And let's go ahead and maybe turn on the faces here. Let's go back to the pre-web app and let's go ahead and pick some nodes. So there are a few ways to do this. I like using the face way. Let's go ahead and adjust the picking sphere size. Oh, that was not right. So here, it's not noticeable, but if you zoom in, you'll see that the picking sphere is really small. So it's a very small sphere. So since the sphere is small, I'll just go ahead and slide it and glide it across these faces. And then once I'm done selecting these faces, I'll select node and I get the equivalent nodes that we want. So let's go ahead and close this. So that's the SPC1 here. So here are the nodes that are constrained. Let's go ahead and look at the force entry if we have one. Here we have a payload 4. Maybe I'll delete that. And then I'll add a new entry called the force entry. Force, create. And let's go ahead and maybe load it here. So let's go ahead and give it a load here. And then maybe a load here also. So force went in there. Let's go ahead and configure this load. Right now the force is going in the positive y direction, but maybe I want it to go in the negative x direction. So let's go ahead and give this a -1 for the direction for both forces. And then I don't know what magnitude to give this, maybe 5,000 units of force. So we have it fixed on one side and we have it a load going in the negative x direction. Let's go ahead and try and run this now. Go to download and upload. Oh, we get another UFM. Let's see if we can identify what the error is here. Search backward keyboard. Oh, what's going on here? Let's go ahead and download the F06 file. So this is going to be a really good demo for any new Nastran users because you get to see what the reality is of playing with a finite element solver. I wish we lived in a world where every physics solver was perfect and you never got an error, but unfortunately we're not there. Oh, okay, so there's an issue with convergence here. I'm just reading the error. So this might be an error that I won't be able to solve in 1 or 2 minutes. This looks like an error that might take 15 or 20 minutes to solve. Here, I'm thinking one thing. Let's see if it works. What happens if I just switch to a SOL 101 analysis, which I don't think will work because PCOMPLS might only work for SOL 400. So we'll see if it works. Okay, we should get an error saying that, hey, this error is only for, or this is only for SOL 400. So let's see what the new error is. So user fatal message. Step command is supported only for SOL 400. Okay, let's do this. We're definitely going off script in this video. Okay, so maybe I'll do this. Let me delete these. I don't know if this will work, so I'm experimenting a lot. So what I'm doing right now is I'm adding the load and boundary conditions to subcase 1. I'm trying to run a linear statics analysis for this example because we started getting errors when we try to use SOL 400. Okay, this looks good. Let's output the F06 file and let's see if we get any user fatal messages. Right now, I'm being told there are no fatal messages. Fatal messages typically get reported in the log file. And then if you look here, there are no user fatal messages. The other place where they get added are the F06 files. So right now, I've downloaded the F06 file so I can fully search the file. And let's see if we get any user fatal messages. We don't. Okay, so that's good news. And now let's go ahead and see if we get some results in here. Maybe we don't. So let's do this. I see we get an echo of the input file. I really don't like that. So let's go ahead and do this. Let's go to commands, configure, and we'll go ahead and say reduce size. Okay. And what was going on is all the commands for outputting data were not there. So let's at the least output the displacements to confirm we actually get results. And let's rerun this analysis. So the whole goal in doing this was to analyze this new configuration. The original model had this. They fixed it on one end, and then they pulled it with the payload 4 here on these element faces. What I went ahead and did was the following. I constrain one side and then I applied a force here. So we're kind of having this bending, if you will. When you have bending, you now have to use multiple elements through the thickness. So that's why I'm going through the trouble of doing all this. Okay, so the run completed. Let's look at the F06 file. Do we get displacements? So now I do get displacements like you see here. I get displacements for each node. Now, why was I doing this? Let's go back to the preview. And let me turn off the element coloring here. So before, let's go to direct now, or the PCOMPLS entry. So we select all of this. So before, we had the direct field set to 1, which was okay in that case because we have one end fixed and the other end was pulling. So this was okay. But then we switched it up a little. We had our layers configured using the third option. So that was this option. So then we loaded it so we have bending. So now all these different layers are taking that bending load. And to do that, you needed to do the following. You need to have multiple elements through the thickness if you want to have bending. So that's what I wanted to demonstrate in that second part of the tutorial. And then I found out we had issues with Sol 400. And then I said, okay, let's try Sol 101. And that worked, fortunately. Okay, let's do a few last things here before I talk about the material coordinate system. Let's go ahead and renumber the angles. Sometimes we're working with layers of positive 45 degrees and negative 45 degrees. So I wanted to show you how to configure that here. So that's what we had. If we wanted to, we could add 10 layers. So maybe let's do that. 10 layers. And let's go ahead and give these G-ply numbers, 8, 9, and 10. We'll use mat 1 for all of these layers. And now the fractional thickness is 0.1. So 45, negative 45, 0, 90, 45, negative 45, 0, and 90. And then maybe 45 and negative 45. So we'll wait for that. So this is what our new layup looks like. And then of course we want to run this and make sure it works. So let's go ahead and run Nastran. And then we should get a complete, okay, things look good. We don't get any UFMs. We'll go to results and look at the F06 file. Perfect. So we get deflections here, and they should be statics, deflections. So there you have it. My apologies that part of the video didn't work out. That's what you get for veering off the script. So there's one last thing I want to talk about, the material coordinate system. When I was looking through some examples, there were some examples that had maybe 1,000 coordinate systems defined. So I think it was the chord 1 or something along those lines to define the material coordinate systems for each entry, or for each element, sorry. Now there is a much simpler way of defining the material coordinate systems. So if you are familiar with C quad 4 and the PCOMP entry, it's very straightforward to define a material coordinate system. If it was a flat, it was something like this. You could just use one coordinate system, CS, to orient the material coordinate system, CS. But unfortunately, with 3D elements, you sometimes have to define one material coordinate system for each element if you have curvature in your mesh, if you will. There is a way to achieve this type of material coordinate system for the 3D elements. So how do we go about that? Let's go back to the pre-web app. Let's go to select entry. Let's go and reset the table, display the descriptions, and let's go and search for PCOMPLS. Here we get told that the NLM options entry has some additional PCOMPLS options available. So we'll create one entry here. And then NL comps, I don't know if it'll be here, but let's look through this. I forget which field it is exactly. Hemicube, I think it started with an L. As ProMap, nope, it wasn't that one. Nope, it wasn't that one. Oh, here we go. I think it was this one. I think it was this one. Let's see if it's selects coordinate system for, okay. Top, use the apply coordinate system. I think it was this one. Oh no, it was not this option. It was the C projection option. So yes, turn it on. When you turn this option on, let's go ahead and display the bulk data entry. So here we have the in lam flag with the second option, which is a chord projection option on. When this is on, it's going to use behavior that's similar to C quad 4 in a PComp entry, which is good for us. So here, let's sum it up. If NLM ops for in lam, if this is off or this is on, or blank, sorry, if this is blank, you would need to define for curved solid meshes, you might need to define thousands of coordinate systems, which is going to take a long time. Or you could use this option. So here you could probably use maybe one coordinate system. Depending on how complex your geometry is, maybe you might need 1 to 5 coordinate systems to help define the material coordinate system. Now, I'm going to stop here because then when we start talking about material coordinate systems, that becomes another 30-minute discussion. So maybe I'll hold off on that for a future discussion. But here I'll say this. Look at this option first. Try to use this option first. If it works for you, perfect. You're going to save a lot of time. What I want to try and avoid is a scenario where we have to use thousands of coordinate systems to help define the material coordinate system for your curved solid mesh. Okay then, so this video went on a lot longer than I was expecting. Maybe that was good because you actually got to see what the process is like for PComp entries. A long time ago, you almost had to use your own imagination to really look at what all these different layers and options were. But thankfully, that's not the case. We have these tools that can quickly show you what the effect is on the PComPLS entry like you see here happening on the screen. So we started off with a PComPLS entry that looked like this. So we had an in-plane load, if you will, or we had a load in this direction. But then we mixed it up. We then configured our laminate to look like something like this. And then we had a force being applied here. At the time of creating this video, we cannot show you the deflections of a PComPLS entry. That's something we are still working on and we hope to have later on this year. Okay then, so let's go ahead and stop there. Let me give you my email address just in case you have a question. So if you have questions about the PComPLS or the PL comp entry, you can contact me. So we're done for today, and as always, thank you for watching.